Okay, so we're going to be doing a recap of the amount of substance topic. So there is quite a lot of equations to this, but also some definitions that we need to be really careful about our wording with. So going to start off by getting us to look at our relative atomic mass. And this is given often with the symbol A with subscript R, so where that R stands for relative and the A for your atomic mass. Now, the way in which we get our relative atomic mass is by taking our average mass of one atom of an element and dividing it by a 12th the mass of one atom of carbon-12, and we can put that into words that our relative atomic mass is the weighted average mass of an atom of an element taking into account its naturally occurring isotopes relative to a 12th of the mass of an atom of carbon-12. So the key points that some of us have been forgetting is that we need to include that it's the average mass. So average, that's where that weighted average, taking into account the isotopes, come into play in this formula. And then also that it's specifically of this carbon-12 isotope, and that we're dealing with atoms of the element. Another mass definition for us is our relative molecular mass, MR, and this is simply the sum of the relative atomic masses of all the atoms present in the molecule. So, as an example, calcium carbonate, our atomic mass of calcium is 40, our relative atomic mass of carbon is 12, and our atomic mass of oxygen is 16. So for calcium carbonate, we're going to be doing 40 for the calcium, plus 12 for the carbon, plus 3, because of that subscript 3, times 16 for the oxygen. And in total that gives us an MR of 100. I'd also like to remind us what the units of these two masses are, and that's that it's in grams per mole. So be careful in a moment when we deal with moles that it's grams and not kilograms as our unit of mass here. So we might need to convert between kilograms and grams when we're doing some questions. The other thing to note is that for ionic compounds, even though they're not molecules, we still use the same symbol MR, and we can still sum up the atomic masses. However, instead of calling it a molecular mass because they don't form molecules, then we call it the relative formula mass. For ionic compounds. So I've already mentioned this word, but a mole is just a number of particles. So just like you might say a dozen is 12, a mole is 6.022 times 10 to the 23. So 1 mole just represents a larger number of particles. So a mole contains 6.022 times 10 to the 23 particles, and this comes about because this is the number of atoms in 12 grams of carbon 12. So just a key point to raise is that this says particles, not molecules and not atoms. So if a question's asking us for the number of atoms, but actually it's part of a molecule, the mole is going to tell us the number of molecules of that molecule, and we can then work out our number of atoms. So I'll give you an example. So in CO2, 3 moles of CO2 is going to be 3 lots of 6.022 times 10 to the 23 molecules. But if I want my number of atoms, well, in each molecule of CO2 we have 1, 2, 3 atoms. So I'm then going to have to times that by 3 again in order to get my number of atoms. So 3 times 3 times 6.022 times 10 to the 23 atoms. So because this moles is referring to CO2, the particles in which it's referring to is molecules. Whereas if we were talking about 3 moles of sodium, well, that would be 3 times 6.022 times 10 to the 23 atoms straight away, as our sodium, our formula is just 1 sodium atom. And thinking about our definition of Avogadro's number, we can get our equation linking mole, a mass, and our relative molecular mass or atomic mass. So here we established that 1 mole is equal to 12 grams of carbon, which has an MR of 12. And so what we're saying here is that our mass is equal to our number of moles times our MR. Often we've seen it written in a formula triangle, and that can work too. And the way in which I always remember it is if I label these A, B and C, and we can fill this in alphabetical order too. So they all really start with M. So MA comes first in the alphabet, so mass, and then we've got moles, MO, and then MR is then last alphabetically. And what we're saying here is that our moles is equal to our mass divided by our MR, our mass is equal to our moles times our MR, and our MR is equal to our mass divided by our moles. Okay, so turning now to look at concentration. So thinking about what it means for something to be concentrated. So if something is concentrated, it means there's a lot of that something in a particular volume. So when we're talking about concentrations, we're talking about the amount of something in a particular volume. Now, the volume which we use in chemistry is decimeters cubed, and this is because it's the equivalent to 1 litre. However, when we are doing experiments, a lot of the time we are working in millilitres, which is equivalent to centimetres cubed. So in order to convert from centimetres cubed to decimeters cubed, we need to divide by 1000 just as we would going from millilitres to litres. So turning now to the types of amounts we get in chemistry. So we've just looked at moles, and we've also talked about mass. So when we talk about concentration, we can talk about concentrations in terms of either our mass in grams per decimetre cubed, or we can talk about it in terms of moles, again moles per decimetre cubed. So in each of these instances we're doing our amount divided by our volume, ensuring that volume is in decimetres cubed, and then our moles, just our number of moles, divided by our volume, which is in decimetres cubed. However, we can also use that triangle we just looked at in order to link these two concentration equations together. So our mass, our moles, and our MR. So what this is saying is that our mass is equal to our moles times our MR. So I can substitute that in to my concentration equation in terms of mass. So instead of writing mass, I can write moles times MR, and that's still divided by the volume, because we're just substituting the mass part. However, we can split up this fraction, as that numerator can come out of the fraction, so that we have our moles divided by volume times by our MR, and this part, you will notice, is the same as our concentration in terms of moles. So linking our two equations together can be done using our MR. So we can times our molar concentration, which is moles per decimetre cubed. Sometimes you'll see the unit M, but that's equivalent to saying moles per decimetre cubed, times it by the MR. Or if we wanted to go the other way, going from grams per decimetre cubed to moles per decimetre cubed, we just need to divide by our MR. I'd like us now to turn to our ideal gas equation. And there's a few laws that came into play in order to derive this gas equation. So our first law found that our pressure was proportional to the inverse of our volume. In other words, that pressure times volume is constant. Our second law found that our volume was directly proportional to temperature. In other words, volume divided by temperature is a constant. And we also found that for a fixed mass, that PV over T is equal to a constant. And we tie this all together to get our ideal gas equation of PV equals nRT. Now this R is our ideal gas constant, and it's a constant, so it has a constant value of 8.31 joules per Kelvin per mole. Now notice the units here, as they indicate to us the units of some of our other variables. Importantly, this k to the minus 1. So k is a Kelvin, and it's on the same scale as degrees Celsius. However, there is no negative Kelvin, so the Kelvin scale starts at 0, which is the equivalent to minus 273 degrees Celsius. So in order to get from degrees Celsius to Kelvin, we have to add 273, because if we added that to minus 273, we'd get to the 0 Kelvin at which our Kelvin scale starts. So our unit for temperature is K for Kelvin. Our N is just our moles, so mole. Pressure is given in pascals. Sometimes a question will give it to you in kilopascals, so there you'll have to do a conversion, remembering that kilo means 1,000. And then finally our volume is given to us in meters cubed. So pay particular attention to these units, as a lot of questions, part of the marks will be for doing those conversions to the units that are required for this equation. Okay, so we're now going to take a look at our empirical and molecular formulas. So our empirical formula is our simplest ratio of the atoms in a molecule. Whereas our molecular formula tells us the precise numbers of each atom in a molecule. And in order to do that, we need to look at the ratio of the moles of different substances in order to get our empirical formula. And then once we have our empirical formula, we can work out the number of units of that empirical formula that are in our molecular formula. So the MR of our molecular formula divided by the MR of our empirical formula gives us the number of units of the empirical formula that are in the molecular formula. In order to work out our number of our ratio of our moles, sometimes we're given data as the percentage of a mass, and so in order to use that we have to divide our percentage by the relative atomic mass of the atom in question. So percentage by mass divided by the atomic mass gives us the start of the ratio of the number of molecules. So dividing our percentage by mass by our AR This is easiest to understand if we look at an example. So taking one from the textbook, so a organic compound containing carbon, hydrogen and oxygen has percentage by mass of 62.07% carbon and 10.33% hydrogen, and so then our remainder is going to be oxygen, which is 27.6, And we then want to consider our relative atomic masses of each of these atoms. So for carbon that's 12, hydrogen is 1, and oxygen is 16. So we can then divide through our percentage by mass by our relative atomic mass to start to look at our ratio of the numbers of atoms. So 62.07 divided by 12 is 5.17, and hydrogen is still going to be 10.33, and then our oxygen 27.6 divided by 16, which gives us 1.725. So we then want to try and find a whole number ratio, so we're going to divide through by our smallest, so by 1.725, as that gives us 1 for our oxygen, and then 10.33 divided by 1.725 gives us 5.988, which is close enough to 6, and then 5.17 divided by 1.725 gives us 2.99, which is close enough to 3. So our empirical formula here is C3H6O. They've also given us the MR of 58, and so in order to find out what our molecular formula is, we can work out our masses of this empirical formula. So 3 lots of 12 plus 6 lots of 1 plus 16 which comes out to be 58, and therefore we know that actually there's only one unit, and therefore our molecular formula is still C3H6O. The final thing I just want to look at is atom economy compared to percentage yield. Now, our yield is our mass of product, and so what our percentage yield is telling us is how efficient our experimental method is, as it compares what you actually yield to what the maximum theoretical yield is. And as it's a percentage, we times it by 100%. Now, things that could mean it's not 100% come through experimental techniques, such as our reactants not being pure, reactants being lost, say, on the side of the beaker, our products being lost through separation processes. If our reaction has a different possible reaction that could happen with the same reactants, may not all happen in that one reaction you want it to. Your reaction might also be reversible, and so your yield may not go to 100% because actually, as you're making it, you're also making your reactions. Our atom economy, however, is telling you how much of your desired product is actually from your mass of your reactants. So it's our mass of desired product over our mass of reactants, and I'm going to add this word here, total mass, because often we forget to include our stoichiometric coefficients when we're working these out. And again, this is given as a percentage, so times by 100%. And if there is more than one product that is being made in a reaction, then your atom economy is never going to be 100%. Equally, if your target is to make hydrogen, your atom economy is always going to be very low, due to that total mass of hydrogen always going to be very low due to the low relative atomic mass of hydrogen. Okay, just to recap what we've covered in this video. So we've looked at what is the definition of relative atomic mass. Why is it called relative formula mass for ionic compounds? What unit are relative atomic masses and MR in? What is a mole? What is Avogadro's number? And what equation links moles, mass and relative molecular mass? So here we looked at what is concentration. We looked at how to convert centimetres cubed to decimeters cubed. We looked at what are the two equations for concentration. We looked at how can we link the two equations for concentration. And then finally we looked at how are pressure and volume related. We looked at how volume and temperature are related, and we looked at how they can tie those two laws together. And then finally we looked at what is the ideal gas equation and what are the standard units to use for this equation. And it's important that we pay attention to the different units, as just having a V there for volume doesn't necessarily mean it's the same units. For example, concentration, we were just using decimeters cubed, but now for volume we're talking about meters cubed. So it's really important that we pay attention to those small factors. We've looked at what is the difference between empirical formula and molecular formula. How do you calculate the number of empirical formula units in a molecular formula? And then we looked at what is the difference between atom economy and percentage yield. And we also talked about why atom economy and percentage yield may never be 100%.